this lecture series about tensor, basic and high level tensor, this lecture series, and this is the first lecture. The first lecture is introduction and some preliminaries about tensor. Okay, now the introduction is before Christ, 300 before Christ, the Euclidean created the geometry of deductive system. Okay, Euclidean जिसे and 1637 René de Perron first 300 BC Euclid created the geometry of deductive system. Any deductive system, the geometry. Now 1637 René de Perron introduced the coordinate system of Euclidean geometry. The coordinate system introduced the coordinate system in Euclidean geometry. Okay. Now at 1901 the mathematician Ricci tensor Levi-Civita mathematician Ricci Levi-Civita Riemannian introduced the curvature of tensor and as so on. So in three-dimensional, now we start the introduction. In three-dimensional Euclidean space, the coordinate system is three-dimensional Euclidean system E3. This is the three-dimensional Euclidean space. Euclidean space. The coordinate system is x, y, and z. Now this can be written as x superscript 1, x superscript 2, x superscript 3. Here 1 superscript 1 stand for x, x superscript 2 stand for y, x superscript 3 stand for z. Now this is the one point, this is the one coordinate point, one coordinate point, and another coordinate point can be written as y1 superscript 1, y superscript 2, y superscript 3. This is another coordinate point. So the length of a vector AB can be written as the coordinate can be written as x superscript 1 minus y superscript 1, x superscript 2 minus y superscript 2. The coordinate of AB vector, this is x superscript 3 minus y superscript 3. So this is in three-dimensional Euclidean space. Now now Zi stand for x superscript I minus y superscript I, where I stand for 1 2 3. Okay. Okay, now this is under summation. This is under summation I equal to 1 to 3, I equal to 1 to 3. This is under summation, but for Einstein convention, this summation does not exist. So this is can be simply written as zi equal to xi minus yi. Now we know the transformation. Now the transformation in the orthogonal transformation at Euclidean three-dimensional space, the orthogonal transformation is can be written as the orthogonal transformation that is x bar superscript 1 equal to L1 x1 plus m1 x2 plus L1 x3 plus a1. Now x bar 2 equal to L2 x1 plus m2 x2 plus n2 x3 plus a2, and x bar 3 equal to L3 x1 plus m3 x2 plus n3 x3 plus a3. This is the orthogonal transformation at Euclidean three-dimensional space. Now this can be written as x bar I equal to Li x1 plus mi x2 plus ni x3 plus ai, where I stand for 1, 2 and 3 for three-dimensional Euclidean space. Now now for orthogonal transformation coordinate system, the AB vector coordinate point is z bar I equal to x bar I minus y bar I. So that can be written as z bar I equal to x bar I minus y bar I so that is Li x1 mi x2, put the value xi bar and yi bar, then we get and ni x3 plus ai minus li y1 plus mi y2 plus ni y3 plus ai. Now we ultimately got li m sorry z1 plus mi z2 plus ni z3, where z1 is x1 minus y1, as so on, as so on. Now this is the some introduction. This is at Euclidean space, three-dimensional Euclidean space, the orthogonal transformation and the simple coordinate and their orthogonal transformation coordinate can be written as, and for Einstein convention this summation we cannot write the summation. This is the summation convention. Here this is the summation, here this is the summation. We read of the summation, then there is no summation. The indices can be written as so on. Now some preliminaries. Now for different system of different order, system of different order, so system of different order, we are given a set of two independent variable. There are two independent variable. The independent variable can be denoted as, may be denoted as x and y. Okay, now more convenient way we can be written as, here this is the two independent variable x and y, so more conveniently it can be written as x subscript I. This is called subscript. This means this I stand for 1 and 2. This is subscript. Subscript x subscript I, this is stand for 1 and 2, and x1 means x, x2 means y. Now this subscript, this can be also written as superscript. So xi, x superscript I, x superscript I, this stands for superscript. So xi stand for, this I stand for 1 and 2. This is x1 defined as x. This is y. This is x2 defined as y. This subscript, superscript indices for the tensor quantavariant and covariant tensor. I can explain the quantavariant covariant tensor, the physical meaning, at the next lecture. So this is for introduction and preliminaries lecture. So this is subscript, this is superscript. Now the this is convention when at the fourth dimension, this is for three-dimensional Euclidean space, x1 equal to x1, x2 equal to x2. But at the fourth dimension Minkowski space, this is -1 1 1 1. This is convention. Then the x naught not equal to x naught, x naught not equal to x naught. This is subscript, this is superscript. Here x naught stand for time component, as c equal to 1, x1 stand for x, x2 stand for y, x3 stand for z. But the x1 equal to x1 for this convention, this is -1 1 1, this is time component, this is x component, this is y component, this is z component, this is the metric. Okay, at the later lecture I will discuss about the whole convention. Okay, now now the tensor means the one magnitude many direction. So the tensor rank 0 is scalar, tensor rank 1 is a vector, tensor rank 2 is a tensor. This is higher tensor rank 4, rank 5, rank 6. There are many rank tensor, but tensor rank 0 is a scalar and tensor rank 1 is a vector. Tensor means one magnitude many direction, and eigenvector or eigenvector means many magnitude one direction, and vector means you should know that is one direction one magnitude, and scalar means is zero direction one magnitude. Now for for rank 2 and 3 can be written as, this is 1 1, this is 2 2, this is 3 3, this is subscript, this is can be written as so on. This is rank 2 tensor, this is 1 1, this is a1 2, this is a1 3, and this is a2 2, this is a3 3, as so on, and this is a1 2. The subscript superscript can indices can be written as rank 1 rank 2 as so on. So that can be written as, ultimately that can be written as, for subscript indices a I j and superscript indices a I j, this I and j indices I equal to 1 2 3 and j equal to 1 2 and 3 for 3 dimension. Okay, now for rank 3 can be written as a I j k, a I j k. For 2 dimension I j k equal to 1 2. For 3 dimension I j k stand for 1 2 3. Now the summation convention. Now the summation convention, the summation convention can be written as I equal to 1 in ai xi. So a1 x1 plus a2 x2 plus as so on an xn. So from the get rid of summation, we can written as ai xi equal to a1 x1 plus a2 x2 as so on an xn. This is called dummy indices. This is called dummy indices. The dummy indices, that indices occur twice and once as lower and indices and once again upper indices. This is called the dummy indices. This is dummy indices. This can be written, this can be changed and written as follow. So the dummy indices. So for any indices can be written as aij, xi, xj. This is dummy indices. This is rank 2 metric or tensor. This is rank 1 tensor. Now free indices. Free indices. What is the free indices? Now some dummy indices can be as shown aij equal to xi, xk. So that can be written as xj and xk. This I and this I contracted by this metric, by this tensor, and we can be written as follow. This is free indices. Thus can be the free indices. The free indices can be expressed as not dummy, not repeated. Okay, the free indices is not dummy or that is not repeated. It is called free indices. This is k, this is j, this is I, this is I. This is called free indices. That is not repeated. Now the Kronecker delta function. Kronecker symbol. The Kronecker symbol particular the system is second order. Kronecker symbol is a second order the Kronecker delta function or Kronecker symbol or Kronecker delta is a second order. So it can be written as delta ij. So delta ij equal to 1 for I equal to j and equal to 0 for I not equal to j, where I and j stand for 1, 2, 3 as so on n. Now some Kronecker delta function property, the variable, some Kronecker delta property or symbol. So 1, if x1, x2, xn are independent variable, they are not dependent anyone, independent variable. So del xi divided del xj equal to 1 when I equal to j and 0 equal to I not equal to j. So there is a x here, the I is a superscript and there is del x, there is j is a superscript. So that can be written as del xi divided del xj equal to delta ij. When I equal to j, that is a 1. When I not equal to j, that is a 0. Now second property. Delta ij delta jk, that can be written as delta ik for, so this indices is equal, then we can contract that indices. So for delta ij delta jk equal to delta I1 delta 1k plus delta I2 delta 2k plus delta I3 delta 3k as so on plus delta I delta ik as so on plus delta in delta nk. So this is 0, this is 0, this is 0, and this is 1, and this is 0. So ultimately we get so delta I k. Here this term delta I k. Now the third property, now the third property delta I that can be represented as delta 1 1 plus delta 2 2 plus delta 3 3 plus as so on delta n. That is called 1 plus 1 plus 1 plus 1 plus 1 plus at n number. So n times 1, so that is n. For 3 dimension delta I for 3D, so that is 3 delta I for 2D equal to 2, and delta I for 4th dimension, that is 4. This is the property. Now another property, the fourth property, the fourth property delta ij delta jk. So these indices and these indices are same, so can be contracted. That can be written as, sorry, this is ajk, that can be written as aik. This is a second rank tensor, and this is a Kronecker delta. So these indices are the same, so that can be contracted as one. So delta 1j a jk. So delta 1 1 a1k plus delta 1 2 a2k and delta 1 in ank. So that can be written as a, this is 1, this is 0, this is 0. So a1k plus 0 plus 0 plus 0 plus 0, and that is a1k. For this, for I equal to 1, and for I equal to 2, I equal to 3 can be written as, for I equal to 2 and I equal to 3, we can written as so on. For a 2k I equal to 2, a 3k I equal to 3, a 4k I equal to 4, a 5k I equal to 5, a nk I equal to n, as so on. So that can be written as aik. This vector can be written as aik. So the fifth property, delta ij, this is covariant tensor. A is a covariant tensor. The covariant tensor and quantavariant tensor, the physical meaning and the mathematics I will discuss at second lecture. Okay, now this can be written as A, J, K. These indices are same, can be contracted. 6. Delta I, K, A, J, I, A, J, K. Okay, these indices are same, can be contracted. 7. Delta I, J, A, J can be written as A. This is a vector. This is second rank tensor. This is a vector. AI. And delta ij ai equal to aj, and 9 delta ij akj equal to ki. These j are the same, can be contracted. So now some result of determinant. Some result of determinant. So a determinant A can be written as, for nth order, this component is aij, that can be written as a11, a12, a1n, a21, a22, and a2n. So that can be written as determinant a n1, a n2, and a n. So this is the homogeneous polynomial at of n degree of in the element. This is n degree, and this is n degree in this element are n degree, and is the homogeneous polynomial. The indices I and j. This is the I and this is the j. The indices I can be denoted as row, and j can be denoted as column. So the determinant is aij mod of aij, and aij. So if aij and now aij now aij equal to aji, this is called symmetric matrix or symmetric determinant. Symmetric. And aij equal to minus of aji, this is called CQ symmetric. CQ symmetric. Now if capital Aij, if capital Aij denote the cofactor of element Aij, the cofactor element of Aij, so in the determinant A, the determinant is A, so then the sum of the product of the element ith row is equal to the A if I equal to j and to 0 is I not equal to j, so can be written as, that can be written as the sum of the product of the element ith row is equal to A, so can be written as A1 this capital A1 is the cofactor of Aij, small aij, the matrix. So plus AI2 A2j as so on plus AIN equal to the determinant of the matrix equal to delta ij. This is the Kronecker delta function and this is the determinant. Determinant of Aij. And this is the cofactor of Aij. So Aik Kj can be written as delta Ij. This is the same indices, dummy indices, so can be contracted. And a kj a jk, these indices are the same, can be contracted a delta ji. That can be written as summation convention, and dummy indices can be interchanged as on. Now the determinant of n square cofactor, the determinant of n square cofactor, this is the n. Now n square cofactor is n square, the determinant of n square cofactor AJI of the element of A called the adjoint of A, and the A is written as AJI and A equal to A to the power n minus 1. At later lecture, as progress the lecture and the later lecture, I can discuss the matrices and many other tensor relation as so on. Now this is the convention or dummy indices for preliminaries lecture. You can understand the dummy indices, that's it. So this is now differentiation of a determinant. Differentiation of determinant of a determinant. Differentiation of a determinant. So differentiation of determinant can be written as del A divided del X equal to del A11 divided del X del 12 divided del X as so on as n component, and A12 A22 as so on, and AN1 AN2 as so on, plus A11 A12 as so on A1n, and this is the first row differentiation. Now that is the second row differentiation, A21 AX del A22 divided del X as so on del A2n divided del X. a n1, a n2, a so on, a n, and so on. Then thereafter the third row differentiation, then fourth row, then nth row, as so on. So that can be written as, for dummy indices, this can be written at the matrices. This is large scale on the paper, but at the dummy indices it can be at convenience as you can. Now at the dummy indices, del a11 divided x a11 plus del a12 divided x a21 plus s1. This is a contracted, this is contracted, and plus del a1 in divided del x a in 1. So that can be written as del a1I divided del x ai1. And so so del a divided del x can be written as del ai1 divided del x ai1 plus del ai divided 2 del x ai2 as so on plus del ain divided del x ain. So del a j del a j divided del x and del a j I divided del x a I j. So these indices contracted, these indices are related. That can be written as. And for y component, for z component, that is the same as so on. Now the linear equation and Cramer rule. For matrices, the Cramer rule we all know. Now the Cramer rule for dummy indices. So a I j x j equal to bi. I and j stand for 1, 2 and n. Now a I j x j a k I equal to bi a k I. So these indices contracted, these indices contracted, as so on. And we assume that aij xj can be written as bi. So a delta kj xj equal to bi a ki and ak a xk equal to bi a ki. So here we assume that aij xj equal to bi. There is nth unknown used in summation convention. Nth term has exist. Let the coefficient of mod aj can be a, and the cofactor of aij equal to aji denoted as, and multiplying by aki. So this is the cofactor, this is the matrix, this is the coordinate, this is the cofactor, this is the coordinate. Now the value from 1 to n can be written as that, and xk can be written as bi a ki divided a, where a not equal to 0. So that's it. Now we do the some example. simple example as related or exercise as related that question. Now one example, if y are n independent function of the variable xi zi are n independent function of yi, and if ui equal to vj del xi and del yj and vi equal to wj del yi divided del zj, where ij stand for 1, 2 and n, then show that ui equal to wj del xi divided del xj. So this is a question. Now we have ui equal to vj del xi divided del yj and vi wj del yi divided del zj. So this is the one equation, this is the two equation. Now 1 and 2 equation we can written as ui equal to vj del xi del yj. Now changing the dummy indices. Dummy indices can be changed any indices. That's could not matter on the mathematics. So j by k dummy indices can be changed. So j by k, so vk, j can be replaced as k, we can replace, so yk, and that can be written as vk, the value of vk, the value of vk is the value of vk is wk. So vk can be written as wk del yi divided del zk. So vk del yi divided del yi divided del yi where is the del yi divided del zk del xi divided del yk. Now 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 ui equal to we can assume that is k convention. Okay, now wk del yi del yi divided del yk del xi divided del xi divided del zk. So so that can be written as wk delta ik del xi del zk. Now that can be written as, this is the Kronecker delta function, so that can be written as wi del xi divided del zk. So for convention we can written as w, the dummy indices can be written as w w oh sorry, then the okay, that is so wj equal to del xi divided del zj. For we can interchange the dummy indices and we can written as. So this is the lecture 1. Now next the lecture about the tensor, quantavariant tensor, covariant tensor and tensor algebra as so on. So for homework, for you should try ex6 ex1. So homework, if aij magnitude is a11, a homework a12, a13, a21, a22, a23, a31, a32, a33 and bij can be written as. Now show that aij bkm equal to cij magnitude, where cim equal to aip bpm. This is homework. So that's it guys, and thank you. You can like, share and subscribe. Like, share and subscribe please.